Good day again, everyone. Welcome to another tutorial by M.I.B. Math is beautiful. And today we'll be looking at proof by counter example. Now, despite the name proof by counter example, this is not really a proof. It is just a way of showing that a statement could not possibly be true. Now, this is done by simply providing an example or a case where the proposition does not hold. It is also to be noted that whenever you are doing the proof by a counter example, it is not enough to just state the counter example. However, you must also explain why it is a counter example. That is how you will actually get full marks for this question. Now let us just consider a statement, right? For all x, which is an element of M, if P of x, then Q of x. Now this is saying that for all x, which is an element of M, if P of x holds true, then Q of x holds true. Now for the counter example, basically, what you'll actually do is that you want to prove the falsity of this statement. And how you do that? There must be a value of x, which is an element of M, where P of x is true, but Q of x is false. So, hence, there must exist a value where x is an element of M, such that P of x and not Q of x. Now, this is the symbol for and in reasoning and logics. You can look out for my tutorial. And if there are any questions that you need answers to, please contact me in the details listed in the description and I'll definitely get back to you. Let us look at the following question. It says, disprove by counter example for all a and b, which is an element of real numbers. If a squared is equal to b squared, then a equal b. Now, as I said in proving counter example, all that needs to happen is that you find a case or a statement that proves the falsity of the proposition that was given, right? So in our case, we are saying that for all a and b, which is an element of real numbers, if a squared is equal to b squared, then a equal b. So we just need to find one case to disprove this statement here. And that one case we're going to look at, there are many numbers that you could use to disprove this, but we'll just take a quick one, right? So we're going to say let a equals 3 and b equals minus 3. A squared equal b squared. This would be equal to 3 squared equals minus 3 squared. 9 equals 9. So this is actually proven true, right? But in terms of a equal b, this would be minus 3, or rather positive 3 equals minus 3, right? However, this statement is definitely not true. So 3 is definitely not equal to minus 3, which implies that a is not equal to b, which is false. So in this case, we have proven that the first statement is true, however, the latter is not, right? So in this case, we have proven that P of x is true, however, Q of x is not. So therefore, this statement is false because a squared is equal to b squared, but a is not equal to b. Question excellently done. Math is beautiful. Let us consider this example. If a sum of two integers is even, then one of the summands is even. Right? So you're looking at two integers. You're looking at the sum of two integers, right? Let m and n be elements of integers. So they're saying that if the sum of two integers m and n is even, then at least one of these must also be even. Now we can use two quick ways to prove this by a counter example. First method is very simple. Just simply find a case that disproves this actual statement. And we can simply use two numbers for let m equals 9 and n equals 7. Right? So m plus n is equals to 9 plus 7, which is 16. However, m and n are odd. Therefore, statement is false and not true. Right? So this is a very simple way to disprove it. Just find one of the cases, just find one case or statement that disproves the entire proposition. Right? Another fancy way that we can actually look at this one question is in a more general notation. Right? They are saying that if the sum of two integers is even, then at least one of the summands should also be even. So we are going to look at the case where none of the summands are actually even. Now if we can recall that odd number is generally denoted as what? 2k plus 1, right? So we are going to assume two odd numbers in the form of 2m plus 1 and 2n plus 1. Right? So basically these are two odd numbers. So all we're going to do is actually add these to get an even number, which disproves the entire statement because these are the forms of two odd numbers. So adding these, we'll actually get 2m plus 1 plus 2n plus 1, which is actually 2m plus 2n plus 2. Right? Now, what we can do is that based on this we can factorize, and this will be 2m plus n plus 1. Now based on this now, this here is an integer, but not just any integer. This here is an even integer. As we recall, odd numbers are in the form 2k plus 1. Even numbers are in the form of 2k. So in this case above, k would have been equivalent to m plus n plus 1, which m plus n plus 1 is indeed an integer, and 2 times any integer is even, linking back to 2k. So therefore the statement is proved false. And this is a nice and easy way to work out a question like this. Now, question excellently done. Math is beautiful. Thanks for watching this video. Please like, subscribe, hit the notification bell, leave your comments, and visit us on Facebook at M.I.B. Math is Beautiful.